First speaker this morning is Nikolay Nikolov, talking about Krull Schmidt theorem for small profinite groups.
Morning. Thank you to the organizers for inviting me. It's a pleasure to be here. And today I chose to speak about a recent result which we proved with Tamar Baron. And I'm very happy about this result because most of my work with Tamar was about very big groups of huge cardinalities. This was one of the results we actually proved for finitely generated profinite groups. So small profinite groups in particular include, as I explained, they include finitely generated profinite groups. So I'm very happy, we are very happy that we proved the result for new result for finitely generated profinite groups. Okay, so a Krull Schmidt theorem. What is a Krull Schmidt theorem? So this is a bit of a vagueness about the name. So there are very different names to this type of theorem. So let me start. As far as I know, the first result was by McLagan and Wedenberg in 1909. They proved the results about uniqueness of direct product decompositions of finite groups. So stated theorem. What we proved is let G be a finite group. So then we can decompose G as a direct product of several indecomposable finite groups. And moreover, the isomorphism types of A1 up to AK with multiplicities don't depend on this decomposition, don't depend on the choice of the decomposition. Choice of the decomposition. Okay, and now, and the proof of this is quite nice. By our standards nowadays, completely elementary. It uses induction on the size of the group, yeah. Now this result then appears improved, has been improved and generalized by many authors. Almost immediately, in 1911, Robert Remak, in his thesis in Berlin, I think, he proved the same theorem again and gave a different proof. Gave a different, and he proved something more general. He proved, in fact, that any two such, for a finite group, any two such decompositions are actually related by an automorphism of the group. And then shortly afterwards, Otto Schmidt improved, basically simplified his proof. And reduced it to something like a 1-2 page argument that is kind of appears now in the standard argument in the textbooks. It's kind of more or less inspired by this simplification of Remak. And then in the 1920s, Vogt and Krull realized that generalized to groups or modules which are not necessarily finite now, but which have both the ascending and the descending chain condition on the normal subgroup. So this is not a complete list of people who have worked on these topics, but these are kind of the main names. And somehow, so when I call it the Krull Schmidt theorem, really this is the theorem that is inspired by all these people. So some books call it the Krull Schmidt, and it has different names, but essentially it's this type of theorem. And immediately you see you need a condition like that to ensure that a group or module will have a decomposition, a finite decomposition as a product of groups. Yeah, if you have the ascending or descending chain condition, then this very quickly prove that any group with such condition has such composition. Okay, so my talk is about profinite groups. What about profinite? Okay. Now, I decided to mention why. This part is maybe not for this audience, but let's just do it anyway. Selling direct products of groups. Well, first of all, direct products of a family of finite groups, with SI finite. This is one of the standard examples of profinite groups. And in fact, this is the biggest example because any profinite group sits inside such a direct product as a subdirect product. Yeah? So direct products are very important in profinite groups too. Another, let me just mention, whenever you have a group with a congruent subgroup problem, for example, S ln Z, its profinite completion is a direct product of its completions over different primes. Yeah. So direct product of these guys, and also direct products of simple groups are one of the kind of families of profinite groups that we understand very well. So here. So when the groups SI are non-cyclic simple, then, for example, we understand when these groups are profinite completions even. Yeah? So we can tell exactly under what conditions such a direct product is a profinite completion. It turns out that this is the result of me and Martin Kasabov, that for direct product of non-abelian finite groups to be a profinite completion, the necessary and sufficient condition is that it has to be topologically finitely generated. I mean, profinite completion of a discrete finitely generated residually finite group. It has to be finitely generated, and the ranks of these groups have to tend to infinity. Yeah, so we understand this very well. Okay. So,
any multiplicity?
Yeah, even if you have multiplicities, as long as it's...
It can also go to infinity.
Yeah, the multiplicity can go to infinity, and then the speed of the growth to the infinity will be related to some power of the sizes of these groups. This will be the condition that they're finitely generated.
Yeah. It can go.
Yeah. So we completely determined necessary and sufficient conditions, but I have to mention that the groups whose completion these groups are never rigid. They have many different non-isomorphic subgroups inside with the same profinite completion. So I should decide to mention this since rigidity is a big topic in this workshop. Unfortunately, this is the opposite here. Yeah. These are never rigid. But anyway, now I should tell you what is a small group. So definition, very easy definition. A profinite group is small if for any integer n, finite group G is small, is for any integer n, G has only finitely many subgroups of open subgroups of index n. So if G has only finitely many open subgroups of index n. Okay, examples. Okay, the most important example is if G is finitely generated. If G is finitely generated profinite, then G is small. Oh, because it can only have finitely many topological homomorphic images of given size, because everything is determined by what the generator go to, and they only find many generators, they only find images. But the converse is very far from true, because for the converse, you can consider a small group which is take the list of the prime numbers, pi, the different primes, p1, p2, etc., and then and just raise take this the cyclic group of size pi to some multiplicity which grows to infinity. For example, to multiplicity pi. Okay. This one is small, but not finitely generated. Its zero subgroups are finitely generated, but okay. Right. Okay, now I should tell you the result. As you can guess, it's the obvious thing, the obvious theorem. Right. So let G be a small profinite group. Then G is isomorphic to a direct product of some indecomposable profinite groups with AI indecomposable profinite. Moreover, if you have two isomorphisms, say with some other collection of indecomposables, composable, then there is a bijection between the factors from I to J, and such that AI is isomorphic to P of Fi for each I. Okay, so it's the natural statement that we would expect. And right, first of all, we are very surprised that we couldn't find a reference to this result, so that's why I'm talking about it.
Is it given by an
Oh, we did not consider that question. We kind of stopped. We were very happy to get up to this point. Yeah, so one can ask, the next question. Is there an automorphism of the group which was sent? But I guess.
maybe not continuous. Or
It sends all of them?
Yeah, it's
it's one-to-one, and then it's defined by the automorphism. Just
No, the problem is continuity.
yeah, we didn't.
continuity is the problem.
Yeah, we didn't consider this at all, so may not be very hard. Yeah.
You probably can take inverse limit of finite array products, construct automorphism there, and then just eat one.
Well, if it is finitely generated, then it is continuous by your theorem.
Yes.
Small groups can have non-continuous automorphisms.
Yes, that's right. Small groups don't have to be strongly complete. Yes. Small groups can still have finite index subgroups which are not open.
Yeah, but still, this doesn't mean that they can have automorphisms which are not continuous. Is it possible that every automorphism of a small group is continuous?
Well, that's a good question, which I
Because it uses permutations.
Is there any natural topology on the index set?
Yes.
Compactification.
So we thought about this and we managed to avoid it. So I can tell you how we managed to avoid it. In the proof, you're going to see that we completely avoided the question about the topology on the INJ. Okay. So let me continue by telling you a few properties of small profinite groups that we use. Okay. So what do we need about small profinite groups? Or actually, no. Let me first tell you why we actually such a result is not true in general. So if you remove the condition that G is small, note now if G is not small, then G may not even have a decomposition. Not be decomposable into decomposable. May not be a product. May not be a product of indecomposables. Even if G is a billion for people. So what's the easiest way to get to something like that is use Puntriagin duality. So for any abelian group G, so when G is abelian, we have its Puntriagin dual, which I denote by G star. So this is basically the group of all characters from G into the circle group. Under multiplication. So if this is a abelian profinite, let's say pro P, then the dual is a abelian P group. So any element has order which is a power of P, a finite order which is a power of P. And this is this correspondence goes back as well. So G is isomorphic to the dual of the dual, right? It's this duality. And direct product decompositions for profinite groups correspond to direct sum decompositions for abelian P groups. Okay? Now, for P groups, there's a theorem due to Kaplansky that the only indecomposable abelian P groups are precisely cyclic groups for N and the quasi-cyclic group CP infinity, which is the union of these all the P power roots of unity. So this is all the complex numbers such that Z to some power P equals 1. Okay. In the dual world, therefore, the only decomposable profinite groups indecomposable profinite, pro P abelian groups are just cyclic groups, the duals of the finite groups here, and the p-adic integers. P-adic integers are the dual of this group. That's easy to see. Okay. And now it turns out that it's actually a bit easier to work with abelian P groups. And one of the first examples of interesting abelian groups, which are not product of indecomposable product of finite groups, was the Prufa group. So let's introduce it. Let's call it a Prufa group, call it P. So this is a group which has a presentation with infinitely many generators in the category of abelian groups, such that x, so I from 0 to infinity, x0 has order p, and then after that each xk is p to the kth root of x0, each k. Presentation. Take a cyclic group of order p, and for each power of p, we adjoin a p to the kth root of x0, the different ones. Okay? Now this group is the kind of standard example of a group which is not a direct sum, because
Sorry, could you flip those to forks?
yeah. Okay. Now it's easy to see that P does not contain Cp infinity, even though the element x0 has roots of arbitrary arbitrary power of p. They're not actually nested inside each other. It's not like you can take p root of a p root of a p root. Yeah, and also, but also p is cannot be isomorphic to the product of finite cyclic groups. A direct sum. Because one important criteria for a group to be a condition for a group to be a product of finite, the direct sum of abelian group to be product of this direct sum of finite groups, is that then P does not have elements of infinite height. So in a direct sum of finite cyclic groups, every element has there's some integer n, so that you cannot extract n roots of that element, because that's true in finite groups. Whereas in this group, by choice, x0 has infinite height. You can keep extracting p to the k roots of it. So therefore, p is not a direct sum of cyclic groups, and therefore its dual is not a product of indecomposable. Okay. And of course, this is not a small group. It's not finitely generated pro P group. Okay, so what are the properties of small groups that we need? I can summarize them. Okay, first of all, proposition. That's the easiest one, is that actually, first, let's say, for profinite group, G denote by f of G the isomorphism classes of the topological finite quotients. Logical finite quotients of G. Forgetting their multiplicity, so we just kind of have a set of these quotients. And it's well known that a finitely generated profinite group is determined by its collection of finite images. But the same proof actually works for small groups. So, proposition, if G is small, profinite of course, then G is determined, determined up to isomorphism by f of G. Okay. So if you think about the proof, you can actually make it work in a collection of small groups. And as a matter of interest, with Tamar, we actually proved the reverse. We proved that this is a characterization of small groups. And a slightly more complicated result, which we call the theorem because it took us about a page and a half to prove, is that conversely, if G is profinite and for any other profinite group, let me just say n determined by its profinite images among all profinite groups, then G is small. Okay. So by determined, I mean that you don't require that the other group is small. So you say for any other profinite group H, which have the same set of finite images as G, then H is small and isomorphic to G. Smallness comes for almost for free actually. Okay. And these are kind of like, for example, here we don't use the classification or anything. There's nothing very deep, deep here though. Still nice.
So you mentioned that small groups can have non-continuous and finite images. So here, what is that? G finite images?
Topological, yeah.
What's that?
Yeah. So quotients by open normal subgroups. Okay. So this is one nice look. And the other result that actually was more useful for us is another characterization of profinite groups using words. And this one is actually a theorem of Siegel. It's the following. A profinite group is small if and only if you take for any integer n, if you take the set of n powers, g to the n, so this is the group generated by n powers of g, and you take its closure, this is open. Again, one direction is trivial, so if this is open, of course, since any normal subgroup of index n contains this group, and this one is open, it has only finitely many subgroups of index n, normal subgroups of index n, and the other direction is more advanced, and ultimately, actually, it needs the all the result on finite groups. In particular, it needs the Zellmanov solutions to the restricted Burnside problem. Right. Right. Just one more tool that we need, and that's about cancellability. Yes. Cancellation properties. Definition. So this is a general definition for any group. We say that group G in some class, in some collection, in some class of groups C is cancelable in direct products, but I'm not going to write it. The word cancelable has many meanings, but here the meaning is cancelable in direct products in C. If the following happens whenever we have two groups B and B1 and B2 in C with such that G times, oh, I didn't have A, so yes, A and B in C, such that if G times A is isomorphic to G times B, then A is isomorphic. Okay. Now it's very easy to see using the theorem, the theorem by Vandenberg, Krull Schmidt, etc. for finite groups, that examples is that any finite group is cancelable in finite groups. If G is finite, then G is cancelable in finite groups. Why? Because of the theorem that I started with. Simply, you're going to decompose all the groups A and B and G into indecomposables, and you're going to match them up because you know that they match up, and then you're going to cancel G. Repeat the same factors on. Right. How, in fact, more, but a slightly a much stronger statement is that, in fact, finite G is cancelable in all groups. So this I found in a paper by Hershon, but he quotes a result of Tarski. The 40s. Okay. And since we are in general questions, it's worth pointing out that the infinite cyclic groups, by contrast, Z is not cancelable. Even in finitely generated virtually abelian groups.
But Z is cancelable in the class of all abelian groups.
Yes, thank you, Jack. this was actually a question of Kaplansky.
By the way, it is cancelable if and only it is profinitely rigid.
Thank you. Yes, that's what I was going to say next. There's a connection between rigidity here and cancelable is the following. So this is whenever you have whenever we have two non-isomorphic finitely generated residually finite groups with z times A isomorphic to z times B. Okay. Then passing to profinite completion, z hat A hat is isomorphic to z hat B hat, of course. And it turns out that you can cancel, that was my next statement, you can cancel small profinite groups in small profinite groups. Yeah, so I'm going to mention this in a moment, I'm going to show this in a moment. But you can cancel this, and then A hat is therefore isomorphic to B hat, but A not isomorphic to B. So I looked at the Hirschhorn example, and it's kind of very close to the bounce-like example. And Martin told me that also bounce-like considered some this trick with taking a direct product with Z. But Hirschhorn then has no reference to bounce-like, and they're more or less in the same year. I think Hirschhorn was 1976, something like that. They were within each year of each other, so. And here, the paper by Hirschhorn gives his affiliation as Polytechnic College of Brooklyn, or something like that. So geographically looks like a lot of close. Yeah. Okay. Right. So, yeah. And what we can quickly deduce from here is that. Yeah. Let me explain the cancellation for profinite groups proposition. It becomes now an easy fact that small profinite groups, if G is small profinite, then G is cancelable. In small profinite groups. So why? Well, suppose that G times A is isomorphic to G times B in small profinite groups. Let's use Siegel's criterion taken into the N. We can factor out the closure of the nth power. So therefore, we can deduce this modulo. This is isomorphic to this modulo. This, right? Just by factoring the nth power, the closure of the nth power elements. But now these are finite groups, and we know that in finite groups, any finite group is cancelable. So I can cancel this. So I deduce that A modulo A n bar is isomorphic to B modulo B n bar. So they have the same set of finite images, or directly you can take the inverse limit of this set. A is isomorphic to B. All right, so now I have almost all the ingredients to tell you the sketch of the proof of our theorem. Now, the first, there will be two different arguments. One is proving existence, and the other one is proving uniqueness. And both require use of small groups, essential use of the group is small. So proof of main theorem, our theorem. So the existence. Here we go. Well, we have to prove that they exist somehow maximal direct product decomposition. So the only really thing we can do here is it's a Zorn-time lemma argument. So we consider the set the set D of all decompositions. So this set is actually consists of decompositions of G as a product of certain non-trivial factors, so which each group non-trivial, and we define a partial order. On decompositions, we say product of AI I in I is smaller than the product of Bj J in J, and these are both G, right? G and this is G. Whenever we have a surjection, whenever there is a surjection for F from J to I, such that basically, let me just say the obvious thing, such that each of the groups in I is actually the product of the Bj's with J in the pre-image of I. So we kind of we simply refine we refine our decompositions, right? So the relation is by refinement, okay? And now we have to show that any chain has a maximal element. Okay. So let right. So we have let certain let's have a collection of decompositions be a chain in D. So okay, let's assume. I mean, in fact, without loss of generality, everything here, all of our index sets are countable because small groups are countably based. So without loss of generality, I can assume that all these index sets are integers, kind of countable. We can. The chain is actually kind of like it is by integers. And we have some maps, yeah, between sets. These reactions given by the relation, and then what we form our set, the dominating set will be the inverse limit. So now let J the inverse limit of these sets IKs. These surjections. What will be the group Bj for each j? So the inverse limit has this property. The universal property of the inverse limit is that maps canonically onto each ik, right? So each map between ik plus 1 or something like that. That's commuting diagram. This. So you have these maps, call them pi k. So each j maps onto each ik with the map pi k. And then for each j in now, for any j in J, I have to tell you what is the direct factor. Well, it will be the obvious thing. Bj will be the intersection of all the groups that appear pi on pi k by k of J. Yeah. So this will be the the direct factor will be the intersection of these. Okay? And now, by its definition, it's easy to see that these groups pairwise commute. So distinct BJs pairwise commute. So we can form a natural map from the direct product of the BJs. We can attempt, right, to map it to G. However, here we run into the question of convergence, and we need to basically to ensure that these groups tend to the identity as J tends to infinity. Let's say that's infinity. What we really need to show is that given any open subgroup of G, or point U of G, there exist only finitely many BJs which are not contained in U. So, so I want to say that BJ is actually contained in U for almost all J. And if I do that, then I have a well-defined map here by taking just the product in any order I like. And basically, this guarantees some kind of a Cauchy condition that it says that one can define the product of elements in different groups, even if they are infinitely many, the product converges to a unique limit. And then we have to prove that this map is surjective and injective. Injectivity is actually quite easy, and surjectivity is actually also not very hard. And let me explain why this is true. It's we have to use somewhere that the groups are small. So obviously, I can replace U with a smaller group. I can replace U with G to the n. So without loss of generality, I can take U to be G to the n bar. So this is where we actually use Dan-Siegel's result a lot, because these are nice verbal subgroup, and they kind of they respect direct products very well. Yeah. Now, if you look at the particular decomposition, IK, the product of IK of AI IK, right? Okay. So this is my G. So again, I'm going to factor G and bar from it, and that has the effect of quotienting this by in each factor. I take the closure of the and the powers of the elements in each of the factors. But now this has finite index. Yeah, this has size some number n. Yeah, depending on this n. But we fix n for the moment, and so now this is some finite number, and therefore at most n of these factors are non-trivial. So therefore we can deduce that a n I to the n bar is actually equal to ai for all except n of the members from ik. Yeah, so at most n of the members on the kth level of the factors are not in I. But then the set of indices j, where j is not in U, is an inverse limit of these. So let me just be precise. So if I define wk to be those indices in ik such that ai n bar is not equal to I. Yeah? So this is a finite set. WK is a finite set of size n. Yeah. And if I look at the size j, so then if I now look at the set W, which is the set of all indices j in J, such that Bj is not in our U is Gn bar, then you can basically see that W is the inverse limit of these WKs. Yeah, there's an extra step here that says a group Bj is not inside U for an open subgroup U, if and only if for all of these groups are not in U. Yeah, being not contained in U is preserved under intersections. Yeah, this is a standard compactness argument. Okay, but now you see that now this is a finite set of bounded size. Therefore, the inverse limit also has bounded size. Okay. So this is one of the key moments where we need smallness. And yeah. Okay, so this is about the existence. Now the uniqueness is equally kind of involved, but at least the beginning of uniqueness is clear using constellations. So to prove uniqueness is sufficient prove uniqueness. It is sufficient to prove the following: whenever G can be decomposed into AI, I, and Bj, J in J within decomposables, AI, Bj. If I choose one of them, so choose n A to be AI fixed and fix, and need to prove that there exists some J in J, such that we can find the factor A among the others. Right? And I claim this is sufficient because the moment you find a factor among the others, then you can cancel it because these are small profinite groups. Okay, and now you have isomorphism between the remaining factors, and this way we can also match multiplicities because now if you have a factor A in a group and look at now look in the second decomposition the number of factors which are isomorphic to A. So now you have cases, so you can have maybe finitely many here and infinitely many on this side. But then these finitely many you can cancel one by one, you can cancel until you have none on one side and non-positive number on the other. Contradiction to this. Yeah. If you have on both sides infinite, you can match them. Bijection. And of course, if they're two finite numbers, but they're different, again, you can cancel until you reach none on one and the other. So really you need to prove this property. Okay? And then here, you kind of have to use similar methods to the finite case. Let me just say what kind of results we need. We're going to basically use projections onto the factors, and you can see this. So for any group A or B, we have so for any AI, we have the injection from AI into G, followed by the projection onto AI again. Yeah. And Now we have similar maps for B as well. Yeah? So this notation also can be extended to the decomposition of B. This decomposition. Okay, so starting with A, I have this. The composition is this is the identity, right? Phi A composed with IA is the identity on A. Okay. But now the identity on G is the sum of the O identity on OPJ composed with the other way around. Identity on BJ G. G. So here I can insert this. So I have IA, I, J, I, J, A, sum. A. Okay. All right. So we have that the identity on some indecomposable profinite group is a sum of pairwise commuting endomorphisms. These are endomorphisms of A, and they pairwise commute. And we need to prove that it basically is sufficient to prove that under these conditions that at least one of these phi A, I, B, J, phi B, J, I, A, this is from A to A, is an automorphism of A. Okay. And we basically took results on finite groups which use similar statements for finite products. So you can show that if you have automorphism, if you have an automorphisms of a finite group which are kind of whose product as automorphism, not a composition but just a product in the group. If the product is an automorphism, and these are kind of these are normal automorphisms, then if the sum is an automorphism, then one of them is an automorphism. So I'm kind of a bit out of time to the details. But at some stage, again, we have to pass from an infinite sum to a finite sum, and again, we have to use smallness in an essential way here. Yeah. And once we get to this stage, it's a very, very easy step to prove. Using the incomposability of A and BJ, you can prove actually this. They just starting from here. This is isomorphism between A and BJ. That's how that proof goes. And I want to finish with an open question about cancelability. As I said, small profinite groups are cancelable in small profinite groups, but what about the periodic integers in all profinite groups? Is ZP cancelable in all propi groups? So we couldn't answer this question. And if you look at the literature for cancelability in J products, you see a lot of results, and you very quickly realize that it's very easy if your group is complicated. For example, if the group is perfect and has trivial center or indecomposable, then it's cancelable in all groups. Yeah, it's kind of several easy propositions. And somehow the hardest thing is to cancel abelian groups. For example, we can prove that free groups, non-abelian free probability groups are cancelable. Easy. Yeah. Using the known theory of probability groups. But yeah, abelian group seems to be hard, so I leave this as an open question. Thank you very much.
Other questions?
Andre, please.
So you said that small groups may not have repetition, but assuming the
We have this also another, I just ran out of time. That was another open question that I wanted to mention. We thought about this and we couldn't find an example. So we believe probably they're not. I believe they must be counterexamples, but we kind of didn't know easily where to start.
Can you say a couple of words about the proof of the other theorem that if you're determined by your finite quotients, then you're small?
Yes. Yeah, so it goes like this. If the group is not small, then it has somewhere you have infinitely many, for some index you have infinitely many factors, normal subgroups of that index, when you take a minimal such n. Okay? And then you fix a composition series for G in G mod n, and you reach a situation where you have your group G and you have a normal open subgroup U, such that below U they're infinitely, so this is some index n1, and here you have index n2, of which under which there are infinitely many normal subgroups of that index. Yeah, and by minimality you can assume that these quotients are simple of all the same isomorphism type, because there are only finitely many groups of the same size. Okay, and then when you intersect them in your profinite group, if you now replace this with the intersection, here you find suddenly if you take k to be the intersection of the ui's, now modulo u mod k then becomes a direct product of infinitely many copies of the same group, and now we start to exploit this group. And then we can, essentially the way we prove it is we prove that if the group is not small, then we prove that there exist profinite groups of arbitrarily large cardinalities which have the same set of finite images. So we kind of avoid the isomorphism question between them by just kind of going to huge cardinalities, basically using this. So the rest is a bit technical, how we construct that group, but I think it's about a page and a half in our paper. So.
But even with the continuum, if it's a pro-countable group, you can construct, I guess.
Pro-countable group, I guess, is what you don't call small, an imperceivement of countable groups. I think even in the continuum, you can construct. We discussed it.
But yeah, we didn't try because
No,
the way we
it's a different
state,
thing. Yeah.
Yeah,
it doesn't.
yeah. If you're asking about finding a countably based profinite group, then we didn't answer that question.
Okay.
Yeah.
We should discuss it.
Yeah. But my feeling is probably it exists, but it will require more work.
Any more questions? Right, let's thank Nikolay again.